Okay, so I will continue now with section 15.1, which is about line integral, motion in space. Just remember, I had a curve C, and this is in X, Y, and Z, and this was my position vector out of T. This was my V of T, and I have V of T, which is a vector, is dr dt. Well, let's say R is X of T, Y of T, Z of T. V of T is X prime of T, Y prime of T, Z prime of T. And A of T is dv over dt, which is x second, this is acceleration, y second of t, z second of t. Now, well, provided the derivative exists. Next, we calculated the lengths. Well, we had the arc length parameter. This is integral from a to t of absolute value of v of tau d tau. This is the arc length parameter. And what is the total length? This is called arc length parameter. This is the distance from the position A to the position T, position at time A, position at time T. And now we notice that ds dt is equal to absolute value of v of t. Now what is the total length? It says the total length is equal to L is integral, you sum the lengths. So you cut your curve into pieces and you sum them over curve, and this is equal integral from A to B, where there's a parameterization here R of t. This is A smaller than t smaller than b, and this is absolute value of v of t dt. By the way, all this works if t is negative. It doesn't matter, yeah. T doesn't have to be positive. So this is the length. Now we said the line integral, if f is continuous, so I'm integrating a function over the curve, and this is equal integral from a to b of f. I evaluate my function, remember f is a function of x, y, z. By the way, it can be also on the plane. It doesn't have to be x, y, z. It can be only x, y. F of r of t times absolute value of v of t dt. And this is how I calculate the line. And this is what, I guess, where we stopped last time. Now I have to want to start talking about parameterization. So how, if I have a curve, how can I parameterize it? Okay, one way to parameterize my curve. So I will start with some, well, famous parameterization. Line segments are kind of common parameterization. Let's say my particle is moving from a point P, so this is x0, y0, z0, and it's moving to another point, x1, y1, z1. How do I parameterize my curve? Let me tell you first that the parameterization is not unique. And you will see next few examples, parameterization. But independently of the parameterization, well, let's say I parameterize a curve somehow and another person parameterize it another way, you will always get, obviously, the same length, the same line integral. But this is something to prove, okay? But this is an exercise. I will not prove it in the lecture. Let's talk about this later. So this is, calls this point P, calls this point Q, and I want to parameterize the motion from P to Q, which means I need to find an equation of the curve. Well, I need to find R of t. which is the position at time t. Now what is r of t? Now let's say this is a point at time t. Let's say m is the position of the particle at time t. But now since m belongs to the segment pq, this means that pm is equal, well, let's say m is equal, so let's say m is a position of the particle. Okay, let's not worry about the time now, because I don't want to, because there's many parameterizations. So let's say m is a point on the curve C. So this means pm is equal t pq. T here is not necessarily a time, yes? So that means pm, the vector pm, is a constant times the vector pq, but since this is in the line segment, this means t is between 0 and 1. Now remember, I want the position vector r of t. What is r t? This is om. Correct? Now I enter the o here. This will be om minus op equal t oq minus op. And remember, I want om. This will be 1 minus t op plus t oq, and then you will get r of t equal 1 minus t x0 y0 z0 plus t x1 y1 z1, where 0 is smaller than t is smaller than 1. And this is one of the parameterization of a line segment. It's 1 minus t, the initial point, plus t, the second point. Another parameterization is arc of circle of radius a counterclockwise. In this case, counterclockwise. So let's say this is my circle and I want to go this way. Now what do you know at time t? What will be here my parameter? I will choose my parameter to be the angle. So in this case, what is r of t? Now the angle is if this is t in this case, then if this is a, then so this length is a, which means this will be equal to a cosine t I plus a sine t j, because this is my y coordinate. But here is t between 0 and 2 pi. It's the whole circle. Now if it's an arc, let's say this is theta 1 and this is theta 2. With this parameterization, r of t will be a cosine t I, this is a is the radius, plus a sine t j. There's no k here, it's 0, which I mean, where t is between theta 1 and theta 2. Now another possibility is graph. Let's say my curve, let's say I have a function here. It's a function, this is y equal f of x. And let's say I'm moving from x0 to x1. So I'm moving from the point x0, f of x0, to the point x1, f of x1. And this is along my function, where x0 is smaller than 1. Then one way to parameterize this is to take x to be t, and then this will imply that y is f of x, which is f of t. So I will get r of t is equal ti plus f of t j, where in this case my t denotes the x coordinates. This is x0 to x1. Okay. Now I can have another case. So this is case, one of the cases, and another case is, let's say it is a function x equal g of y. Say I have this. And now this is a function, x is a function of y. And let's say I'm moving from the point, this is y0, and then this is g of y0, y0. And now if this is y1, this point is g of y1, comma y1. One way to parameterize it is to take r of t. Remember, this is r of t. If I take t to be my y, so tj, then my x will be g of t. And this is where t, now my t is my y, so my t moves from y0 to y1. And these are the three, well, I think I did 4 main parameterizations. You can have other cases. Now a remark which I was explaining, so remark, a parameterization is not unique. A parameterization is not unique. Let's take, for example, the parabola. This is y equal x squared, and I'm moving from the point 0, 0 to the point 1, 1. One way to parameterize it is to take r of t. Here this is y equal f of x. I take ti plus t squared j, where 0 is smaller than t, smaller than 1, because my x is between 1. But another way to parameterize it, so this is one parameterization. Another way to parameterization is to r2 of t to take 2ti plus 4t squared j. But here my 2t is x, so my t is between 0 and half. But whether I integrate, so these are two parameterizations for the same curve. But notice that if I integrate integral of c f ds, let's say f is any function. This will be, f is any function where f is continuous function, f of x, y. Well, let's prove it since we have some time. Well, so by definition, if I use R1, this would be integral from 0 to 1 of f of x of t of f of t squared times absolute value of v1 of t dt. But what is v1 of t? v1 of t is the derivative of r1 is 1 to t. So this is equal integral from 0 to 1 of f of t squared, and then what is the speed? What's the absolute value of v1 of t? Is square root of 1 plus 4 t squared. Is square root of 1 plus 4 t squared dt. But what if I use the second parameterization? So using R2. So you will get integral over c of f ds is equal integral from 0 to half of f of R2 of t. But here R2 is 2t for t squared times v2 of t dt. But what is v2 of t? v2 of t is 8t. So absolute value of v2 of t is equal square root of 4 plus 64 t squared. So this is nothing but integral from 0 to half. I will put 4 outside, so this will be 2 square root of 1 plus 16 t squared. So this is 0 to half 2 f of 2t 4t square square root of 1 plus 16 t squared dt. Now these two integral doesn't look like the same, but it contradicts the definition. I told you that the definition should work on all parameterization, correct? So this means, so are these two integrals equal? Yes, because notice that if you take the change of variable tau equal to t, you will have d tau equal to dt, which is 2 dt. Then this integral will be equal integral. If t equals 0, tau equals 0. If t equal half, tau equal 1. F of, what is 2t? 2t is equal to tau. 4t squared is tau squared. And now square root of 1 plus, so if tau equal 16, if tau equal 2t, then t equal tau over 2, then t squared equal tau squared over 4, then 16t squared equal 4 tau squared. So 1 plus 4 tau squared. Now 2 dt is equal d tau. And I got back my original integral. So the integral is independent of the parameterization. But what is the difference between this parameterization and this parameterization? There is a difference. This one tells me that the particle is moving from the point 0, 0 to the point 1, 1, which move in 1 second, let's say, in an interval of time of length 1. This one is telling me that I'm moving along the path with time half. So this parameterization gives me a larger, I expect this parameterization is telling me that it's the same curve, but it's traversed quicker, which means the velocity will be larger in general. But the line integral will not change, and definitely the length will not change. Now another case, let's say another example. Let's say I have the arc of circle of length 1. And this is in the anti-clockwise direction. This r of t is equal cosine ti plus sine tj, where 0 smaller than t smaller than pi. I took t here is the angle. But another parameterization is also, you can take, this is cosine 2ti plus sine 2tj, but now my t will be between 0 and pi over 2. Yes, because I took here 2t to be the angle, so 2t equal pi, so t equal pi over 2. These are two parameterization of the same. Which one is faster? Definitely this is faster. And you can notice here, what is v1 of t? v1 of t is, well, what is v1 of t? This is equal minus sine t cosine t. So this implies absolute value of v1 of t is equal square root of minus sine t squared plus cosine t squared, and this is equal to 1. What about v2 of t? This will be equal minus 2 sine 2t, 2 cosine 2t. So this gives me v2 of t equals square root of 4 sine square of t plus 4 cosine square of t, which is equal to 2. So the speed at time t is faster, is larger. So this parameterization gives me a larger speed. Now, here I'm telling, so let's go back to some parameterization. So in this case, let's say in the case of the circle, I'm parameterizing in the anti-clockwise direction. In this curve, the graph, I have my particles moving from the left to the right, from smaller x coordinate to the smaller large coordinate. In this in this case, I'm moving upward. So I'm moving from smaller y coordinate to the larger y coordinate. What if the path is the reverse one? So what if I'm moving, for example, clockwise on a disk, or I'm moving from right to left on a curve? So let's So today's lecture is a bit technical, but we have to do this in order to complete this section. So reverse path. So let C be a curve from A to B, parameterized by the vector r of t equal x of t I plus y of t j plus z of t k. So this is my A, this is my B, and this is how I'm moving, and t is between A and B. Now we denote by minus c the path with opposite orientation, i.e. same trajectory but from B to A. Please, this is just a notation. So if this is C, then minus C is from B to A. So what is, now I want to compare, so compare integral over C of f ds and integral over minus C of f ds with f continuous. So what is the difference? Does the length change? Well, does the inline integral change? You should know that it doesn't. Why not? Let's say f equal to 1. Then this integral will give me the integral of this path. And this integral will give me the length, of this path. And this integral here will give me the length of this path. But the lengths of these two paths are equal because it's the same trajectory but different direction. This is if f equal to 1, but let's prove it in general. So first of all, how to parameterize? Let r star of t, okay, let's find a parameterization of minus c. Okay. Now I know that the parameterization, call it r star. There's, as I told you, there's not only one parameterization. You can find as much parameterization as you want, but let's find one of the parameterization. Now I know, let's say, a parameter C on the same interval. AB. Doesn't have to be, but let's find one of the parameters. Now I know that R star of A, which is at the initial time, R star of A is a point B, which is the same as R of A, R of B, correct? This is the end point here. What about R star of B? R star of B is, because this is R star and this is a parameterization of R star, so at the last interval of time, at the t equal B, at the last moment of time, this is equal to A, and this is equal to R star of B, and this is equal to R of A, because this is the initial point of A. Now in general, I want, if this is, so I will, if this is for R star, this is A, B, this is A, B. Okay, and this here goes R star, it's on this interval, and R is on this interval. I want R star of A to go at the same point where R of B go. Yes, because I know that R star of A goes R star of A equal to R of B. And I know that R star of B is equal to r of a, correct? So this point here goes to a, and this point here goes to b, correct? And this point here, I wanted to go to the same, well, a goes to here, so this point here, which is r of b, I want to go to b, and this point here goes to a. So let's say, so the point here, let's say I have time between, t is between a and b. I want r star of this time interval t to be r of something else that is between a and b. So what is the easiest function between, from the interval ab to the interval ab? You can choose any injective function because each point is traversed once here. Then I can define r star of this point of this moment of time to be r at this moment of time, and r star at this moment of time to be r of this moment of time. So this will be r star of t will be equal to r of phi of t, where this is the line phi of t. Now you can all calculate the equation of a line. This is r of a plus b minus t. Please double check that the equation of this line is a plus b minus t. And this is a parameterization of the parameterization of the reverse path minus c. So what I'm proving here is that these two are equal, and once I prove it, you can use it. Okay. So let's see. So I know this is r star, and I want to calculate integral over c over minus c of f ds. This is equal integral from a to b of f of r star of t, absolute value of v star of t dt. Now I know that r star of t, I already proved it, is equal r of a plus b minus t. But what about v star? Remember, v star of t is equal dr star dt, which means I need to differentiate this function with respect to time, which is the derivative of this function with respect to time. But now by chain rule, I differentiate what is inside. This is minus 1 with respect to time. What's the derivative of a plus b minus t with respect to time is minus 1 times dr dt, evaluated at a plus b minus t. So this means that v star of t is equal minus v of a plus b minus t. So it is the same velocity vector but the opposite direction. So v star of t as a speed is equal absolute value, the minus cancel, I mean not cancel, the minus, since absolute value it becomes plus. So this, then you get integral over minus c of f ds equal integral from a to b of f of r a plus b minus t v of a plus b minus t dt. And remember, I want to reach integral over c of f ds. So how do I do this? I take tau to be a plus b minus t, then d tau is equal minus dt. And this will be equal integral. Now if t equal a, tau equal b. So this is tau equal b, 2. And if t equal b, tau equal a. And then you get f of r, a plus b minus t of tau times absolute value of v, a plus b minus t is tau. What about dt is minus d tau. Now I flip the order of the integration. This will integrate from a to b of f of r of tau, absolute value of v of tau. Since I flipped, I need a minus, but there's a minus here, so this will be d tau, and this is nothing but integral over c of f ds. And now it's so, although you know only how to parameterize, Okay. So although you know how to parameterize a circle with opposite orientation, with anti-clockwise orientation, if there's a question where the motion is clockwise, do I need to parameterize it? No, I don't need. I calculate as if it's anti-clockwise, and then I say since the line integral of a function is independent of the, well, it's not independent of the path, it's independent of the orientation, which means whether it's reverse or whether it's in the direction, in a certain direction or it's an opposite direction, the same integral, then you get the same answer. So you only need this parameterization. You only need the anti-clockwise parameterization. And even if the motion is clockwise, this in order to calculate the line integral. So this is the end of this section. I'm not sure if there's, well, yes, there's only one more thing, and then we're gonna do an example and finish up with this section. So what if my curve is, so union of curve, let's say C is, I have C1 in this case, and then I have C2, and then maybe I have C3, and I have C4. So each curve ends where the next one starts. So we say C is C1 union C2 union C3 union C4, which is the sum, well, the union of these curves. So it's the complete motion from this point to this point. Then integral over C of f ds, the integral over the whole thing. Maybe I know how to parameterize this one. This is a line segment. This maybe half a circle. This is a line segment. I know how to parameterize each one of these. I don't have a parameterization for the whole thing, but this doesn't matter. This is integral C1 f ds plus integral over C2 f ds plus integral over C3 f ds plus integral over C4 f ds. So I calculate the 4 pieces. I mean, this should not be a surprise, because the length of the whole thing is the length of the first curve plus the length of the second curve plus the length of the third curve plus the length of the fourth curve. Okay, let's do an example. Let C be the closed loop. There will be only one video today, starting, well, it will be a little bit longer than half an hour, from 0, 0 to 2, 2 along y equal x cubed over 4 and back to 0, 0 along the line segment y equal x, and let fxy be equal y plus x cubed. And the question is find integral over c of f ds. So C is a loop, okay? So it's very important to know how to draw it. So I start at 0, 0, and then I end up at 2, 2. So this is a point 2, 2. And this is along the curve y equal x cubed over 4. So this is y equal x cubed over 4. And then I go back to 0, 0 along the segment y equal x. So C here is C1 union C2. It's obvious a union of two curves, where this is my C1 and the line segment is my C2. So about my C1, so integral over C of f ds is equal to integral over C1 f ds plus integral over C2 of f ds. So at first I calculate integral over C1 of f ds. I want to parameterize it. So C1, now this is along the curve y equal x cubed over 4, so y equal f of x. So this is r of t. I take x to be t, I, and then y will be t cube over 4j, and then 0 is between, and then t is between 0 and 2, because the x coordinate is between 0 and 2. So I need to calculate integral over c1 of ds, I need the velocity and the speed. So r of t, when I calculate, I will write it this way. So what is v of t? It is the derivative. It is 1, 3t squared over 4. Then what is the speed? It is square root of 1 plus 94 over 16. Then integral over c1 f ds is equal integral from 0 to 2, because this is t equals 0, this is t equal 2, okay, of f of rt, don't forget I will write this as r1 because this is c1, r1 of t, v1 of t dt. And this is equal integral from 0 to 2 of f, well, what is f? Did I write what's f? F is y plus x cubed. Remember, f is y plus x cubed. So it's integral from 0 to 2. My y, it's f of r1 of t. So my y is t cubed over 4. So t cubed over 4 plus x cubed, my x is t, plus t cubed, this is f of r1 of t, times square root of 1 plus 94 over 16 dt. So this is equal 5 over 4 integral from 0 to 2 of 5 over 4 t cubed integral of 1 plus 94 over 16 dt. But notice that here I have t4 and here I have its derivative, which is 4t cubed. I mean, but there's a 4 missing. So I take u to be 1 plus 94 over 16. Then what will be my du? It will be, I differentiate this, it will be 90 cubed over 4 dt. So I have, so t cubed dt, so this gives me that t cubed dt equal 4 over 9 du, correct? So this integral is equal integral. When t equals 0, u is equal 1. When t equal to 2, 2 power 4 is 16. 16 over 16 cancel out, so this is 10. Now, square root of 1 plus 94. 1 plus 94 over 16. I will keep the 5 over 4 for the moment. 1 plus 9, this is u, so this is square root of u. T cubed dt, so this is a reminder on integration. So what is t cubed dt times 4 over 9 du? So this is equal to 5 over 9 integral of square root of u, but square root of u is u power half. So this will be u power 3 half over 3 half between 1 and 10. So this will be 10 over 27 u power 3 half, with 10 power 3 half minus 1 power 3 half. And this gives me 10 over 27, 10 square root of 10 minus 1. Am I done? No, I still have C2. Now what is C2? So I want integral over C2 of f ds. And C2 is the line segment joining the point 2, 2 to the point 0, 0. And this is along the line y equal x. There's many ways to do this, or I will use the line segment formula. Or you can do it over, this is the function y equal x, but in the opposite direction, but it doesn't matter. You can still, you know, by reversibility of the path, you can still solve it. But let's train you for the line segment parameterization. One way to parameterize this, it will be, remember, it's 1 minus t, the initial point 2, 2, plus t, the last point 0, 0, where 0 is smaller than t, smaller than 1. and you do it. Okay, you can solve it this way. But I will use the reversibility of the path. This is do it at home. Okay. Now, or use reversibility. And I know that integral over C2 of f ds is equal to integral over minus C2 of f ds. But what is minus C2? It is the line segment from 0, 0 to 2, 2. What is a parameterization of this? This will be equal, so this is y equal x. So this will be, I take x to be ti plus tj. Because if x equal t, y equal t, where 0 smaller than t smaller than 2. You couldn't have done this here, because then your t will be between 2 and 0. Okay? And t, I mean, we should always take an interval where this is a smaller number, larger number. Now, what is v2 of t? This will be, so this is t. Now, v2 of t is 1, 1. So, absolute value of v2 star of t equals square root of 2. Then integral over c2 of f of minus c2. I have integral over c2 of f ds, integral minus c2 of f ds, which is equal to integral from 0 to 2 of f of r2 of t. Remember, f of r2 star of t times v2 star of t dt. It's absolute value. Remember, f of xy was y plus x cubed, I guess. Okay, it's blocking. Let me check my notebook. It is y plus x cubed. Yes. So f is y plus x cubed. So this will be equal integral from 0 to 2. My y is t, my x is t. So this is y is t, x is t, so plus t cubed times square root of 2 dt, and this will be equal to square root of 2 times t squared over 2 plus t4 over 4 between 0 and 2, and this is equal to square root of 2 into 4 over 2, which is 2 plus 4, which is equal to 6 square root of 2. Am I done? No. So conclusion, integral over c of f ds, which was the total thing, is integral over c1 of f ds. c was this plus this, plus integral over c2 of f ds, where c1 was only this, c2 was only this, and this will be equal to 10 over 27, 10 square root of 10 minus 1, plus 6 square root of 2. Okay, one last example. You know, there's no recitation in this summer class, so I'll do more examples than I usually do in a regular semester. Okay, I have a wire lies along C defined by the parabola x equal y square from 0, 0 to 4, 2 with mass density delta xy equal e to the y over square root of 1 plus 4x. Calculate, well, the mass, the total mass of the wire. So when it say mass density is kilogram or gram or whatever, it's mass over unit length. So I have a wire. This is x equal y square, and I have from the point 0, 0 to the point 4 and y equal 2. So this is to the point 4, 2. And this is my y. So how do I find the total mass? So the way you find total mass is you divide it into small pieces and you find the mass of each piece. But what is the mass of each piece? What is the mass in general? It is density times length. Yes, because this is the mass per unit length. So it will be delta xy times the length, which is ds. And now I have to sum. And this will be the mass. This is the formula of the mass. It is density times small length, and then summing it up would be this line integral. And now this is nothing but now a line integral of the function xy. So I need to parameterize. So this will be integral. Well, I need to parameterize first. Now how to parameterize this curve? This is a function. This is x is a function of y. So I take y to be t, and then my x will be y squared, which is t squared I, and this is equal to t squared t, and my t is this is my t here. It's on the y axis. My t is between 0 and 2. Then what is my v of t? It will be 2t, 1. So my speed will be square root of 1 plus 4t squared. And this implies that the mass is equal integral from 0 to, well, integral over c of delta ds, which is integral t equal a, t equal b, 0 to 2. F of rt, delta xy, is e to the y over square root of 1 plus 4x. You go to r, this is my x, this is my y. So it will be e to the t over square root of 1 plus 4t squared times absolute value of v of t times square root of 1 plus 4t squared. Because remember, this is integral from a to b, delta of r of t, absolute value of v of t, dt. This is what I'm applying, dt. This will cancel out, and then you'll get e to the t between 0 and 2, and this is e squared minus 1. So this will be the end of section 15.1. Okay, and so you can, I will post a handout. You can find now the handout, and tomorrow we'll start a new thing, which will be integral of a vector field, not of a function. Okay. I will also post, I guess, the first problem set, which is, yes, I will post I'm not sure if the first problem set is includes 15.1, 15.2, but if it includes 15.1 only, I will post it. If not, I will wait till 15.2 till we do 15.2. Okay, thank you all, and that would be it for today.